Hello everyone. In this lecture I shall discuss the series of complex functions. Just as before, I have provided a link to this video in our Google Classroom. I have also uploaded the slides in our Google Classroom so that you might be able to watch them later on your personal devices, or maybe print them out if you wish to. This is the plan for this lecture. I shall first introduce you to sequences and series of complex functions. You would find that these ideas are basically extensions of the same concepts involving real functions. So once we have a series expansion of a function, we are next interested in whether that series converges or not. So I shall briefly touch upon the convergence of complex series. Then I shall discuss a special category of complex series which are known as power series. The importance of power series would be evident when I introduce you to the theorem, to the related theorems to these specific series. This would then bring us to the Taylor's theorem, which essentially tells us how to extend the Taylor series expansion in the case of complex functions. Finally, I shall bring singularities onto the stage, and this would then allow us to arrive at a more general Laurent series. So let us first start with the idea of a sequence of complex functions. So let us say I have one function u1 of z, another u2 of z, and so on. So let's say we have a lot of these different functions of complex numbers z, and I denote these set of these functions, I just denote it as un of z. So this is a sequence of single valued functions, and all of these functions, they are defined in some region of the z plane. So we can define what is known as the limit of the sequence. The limit of the sequence, this is the formal definition of the limit of the sequence. It is basically says that if I give you if suppose you give me any positive number epsilon, then we can always find an integer number n. In general, this n will depend on epsilon as well as the value of z, such that the difference, the modulus of this difference would be less than epsilon for all values of all integer values which are greater than this n. So basically, you give me an epsilon, I can always give you an n, such that this condition is satisfied for all integer values which are greater than the n that I have provided. Then if that is satisfied, then this function, okay, this function is known as the limit of sequence, and we write that limit of un of z is equal to capital U of z. Now this is the formal definition of the limit of a sequence. If in the exam you are asked to write down the limit of a sequence, the definition of the limit of a sequence, this is what you will write. Graphically, what this means is this. So these set of functions that I have over here, they are denoted by these regions. If you recall one of those lessons that we had in the classroom, I had demonstrated to you what a complex function really is. So if in the z plane I have a certain region over which a function is defined, that will lead to another region, probably another region in the z plane, in the same z plane. Okay, and we say that there is a functional relationship between these two regions. So for the same z values, we get one region over here. So this is our function, this region represents our function u1. Similarly, this region represents our function u2, and so on. So in general, the ith function will be this. Now this limit which I am saying, that limit is capital U, this is this function which is defined, which is which exists in some other region. Okay, so again, all of these functions, they are all functions of z. So the z is common, so we could have some region over here, let's say here, and this region contains all our z values. So for each and every z value, okay, this function will take value here, this function will take value here, this function will take value here, and this function will take the value here. Now we say that this function is the limit of this particular sequence of functions. When does that happen? Okay, the definition is already given here, but graphically what happens here is basically this. Suppose you give me a small number epsilon. Okay, epsilon is an extremely small number. You give me a number epsilon, any number, okay, any vanishingly small number epsilon. Then I can give you integer number capital N. Okay, so this is what you give me. You give me an epsilon, I give you an integer capital N, such that if I take any integer which is greater than this capital N, okay, so if I have any integer which is greater than this capital N, for that small n which is greater than capital N, I can find a corresponding function. Okay, So let's say this is that corresponding function. Okay, this function we call it u small n, where small n is greater than capital N. Okay, so you have given me epsilon, I have given you a capital N, such that any integer value, okay, which is let's say small n, that will have a corresponding function un, and this function also belongs to that same sequence that we are talking about, such that if I choose the value of z, one particular value of z, that z will give us one value in this function and another value in this function. The difference between these two, okay, so because this is basically ultimately this is going to be a complex number, this will also be a complex number. Difference between two complex number, if I take the modulus, that will give me just the distance between the two. So this quantity is nothing but the distance between these two. That distance will be less than your epsilon. Okay, so now suppose you give me, you said that okay fine, I'll give you a different epsilon, you give me a different epsilon, then if I can give you another different value of capital N such that this same condition is there satisfied, then no matter how small value of epsilon you can give me, I can always find you an N such that these there is going to be members from the sequence, so that each and every member, it gets closer and closer to this. Okay, so if that happens, then we say that this function capital U is the limit of this particular sequence of functions. Okay, so basically this definition is basically talking about that as well, that only. Okay, so in this case we say that this particular sequence, we say that it converges to this function capital U of z. Okay, so now using this original sequence of functions, okay, now remember what is a sequence? Sequence is basically a set of functions. Okay, so we have an original set of functions. Using this original set of functions, we can build a new sequence. That new sequence we call it as capital S n, okay, which will have subscripts n. So how do we define this capital Sn? Okay, when n equal to 1, that is the same as the first element. You can see here, okay, the first member of this sequence is u1, second member is u2, and so on. So if you put n equal to 1, that is equal to the first member of this sequence. If I put n equal to 2, it is the sum of the first two members. So in other words, S2 is nothing but S1 plus U2. Okay, so similarly what will be S3? S3 will be S2 plus U3, so which will be U1 plus U2 plus U3, and you could go on like this. So in general, Sn will be the sum of the first n members of this original sequence. Okay, this original sequence, the first n members from this sequence, you just add them up together, that is going to give us one member, the nth member of this new sequence. Okay, and you can see here this new sequence, it is basically the sum of members of this, so it is known as the partial sum. Okay, so this members of this sequence are known as the partial sum. So Sn is known as the nth partial sum of the first n terms of the original sequence. Okay, and S infinity is known as an infinite series, because if I replace n with infinity, that means if I'm taking infinite number of elements from the original sequence and I'm just adding them up. So that's basically the definition of an infinite series. So now convergence or divergence. So if suppose I have this partial sum, okay, so I have this n partial sum, and in this n partial sum, this subscript n, if I take it as the limit as n tends to infinity, if this is equal to S of z, then we say that the series is convergent, and S of z is the sum of the infinite series. The same definition of the convergence that we have seen here, the limit that way, right? So in this case, capital U was the limit of this original sequence u n of z. In a similar way, we have another sequence, which is S1, S2, capital S1, S2, S3, and so on. That particular sequence will have a certain limit. That limit is S of z. Okay, so that's what we are talking about here. Okay, so capital, so when I take S, that is n tends to infinity, this Sn of z, it will tend towards this capital S. Then we say that the series is convergent, and S of z is known as the sum of the infinite series, and we write, okay, the sum of the elements of the original sequence. So you just add them up together. You can see the sum, it goes, n goes from 1 to infinity, that is equal to S of z. If this condition holds good, then we say that the original sequence is convergent. If this condition does not hold good, that is you cannot find a sum like this, then we say that the series is divergent. So if a series U of n, it converges for all points in a particular region, then that particular region is known as a region of convergence of the series. So this is an important idea that we are interested in when you're talking about series. The region of convergence, that is in for which all values of z does that particular series representation, does it converge. Okay. So now let's talk a little bit about this convergence. What is this convergence? Okay. So if you recall the definition of the limit, so if you give me an epsilon, I can always find an n such that for all n small n greater than capital N, this difference is less than the epsilon that you have given. So if that happens, then this u of z is the limit of this sequence, and we say that the sequence un is said to converge to capital U of z. So now I had mentioned earlier, okay, when we discussed this, we had mentioned earlier this capital N, it in general it depends only on epsilon as well as z. That means it depends on the epsilon that you have given, and it depends on the particular value of z. So for different values of z, the value of n, I'll have to choose a different value of n probably. Okay. So if n depends only on epsilon and not on the particular value of z. Okay. So in the diagram that I have shown you, let me just go back to this diagram once. Okay. So this diagram. So if I choose one particular value of z, okay, that particular value of z, it gives me a point here and it gives me a point over here. This is the difference between them. That difference is less than epsilon for this particular chosen value of n. Now in general, this n depends on the epsilon and it depends on the value of z, which has given me these 2 points. Okay, that is what happens in general. But if it happens that this n, it is independent of the z value, okay, the z value that we have chosen that gave me this, then we say that the series is it converges uniformly. Okay, so that is the concept of uniform convergence. Okay, so if this n depends only on epsilon and not on the particular point z in R, that is the region of convergence, then the sequence is said to be uniformly convergent on u of to u of z for all z in R. Similarly, if the sequence of in a similar way, this is for in general any sequence. So if I from any sequence I get as the sequence of partial sums, okay, and the same thing happens in case of the partial sums. That is Sn of z, it is uniformly convergent to S of z. That means this convergent, that parameter n which you have given, which depends on how you the epsilon value that you have given. If that n is independent of z, then this sequence of partial sums, we say that the infinite series u of n is uniformly convergent to S of z in the same region. So this is the idea of uniform convergence. Okay, the condition for convergence, okay, that whichever parameter that n that I give in response to your epsilon, that n, if it is independent of the specific point z, then this convergence is said to be a uniform convergence. Now coming to absolute convergence, this is really important because you see a series, suppose I have a series summation of un where n goes from 1 to infinity. This series is said to be absolutely convergent if corresponding to this series, if I take another series, that is each and every element of u in this series, I replace it with its modulus. Okay, so let's say I am having sine nx. Okay, so sine nz. Okay, so first one will be sine z, second one will be sine twice z, third one will be sine thrice z, and so on. Now what I do is, if I take the modulus of this, so in this one the first element will be modulus of sine z plus modulus of sine twice z plus modulus of sine thrice z, and so on, that corresponding series. Okay, so if that corresponding series it converges, then we say that this original series is absolutely convergent. Okay, so in other words, series u of n is said to be absolutely convergent if the other series, which we get by taking the modulus of the individual members and adding them all together, if that series converges, then the original series also is said to be absolutely convergent. And there is something called as conditionally divergent. Okay, conditional divergence is basically this. Suppose I have this original sequence. This original sequence, it converges, but the sequence of the absolute values of the modulus of the functions, it does not converge. Okay, so if this does not converge but this converges, then this function is series is known to be conditionally convergent. What about the other way around? Okay, the other one, suppose this converges, okay, then what do we say? Then that leads us to the theorem of absolute convergence. Okay, what theorem of absolute convergence, what it says is this: An absolutely convergent series is always convergent. That is, suppose I give you a series and then I take the modulus of the individual members, add them up together, that gives me the new series. If this series converges, then it is guaranteed that the original series will also converge. But the other way around, it does not always hold good. Okay, the other way around, if suppose the original series converges but the absolute series of absolute values does not converge, then in that case this is known as conditionally convergent. But if the series of the modulus of the members it converges, then the original sequence is, or the series of original sequence is also going to be convergent. So that's the theorem of absolute convergence. Now all this is good, but are there any ways by which we can test whether a series is converging or not? So there are certain special tests for convergence. Okay, first test is, I'll give it to you in the form of theorems. Okay, so the first theorem is known as the comparison test. Okay, so comparison test is basically this. There are two parts to this theorem. The comparison theorem is basically this. Suppose I want to know if this series un, I want to know if this series un, if it converges or not. Okay, so what I can do is I can compare this to some other series which I know is all which is already absolutely convergent. Okay, so there is some other series vn, and we know that this vn is absolutely convergent. Why? Because the sum of the series of the absolute the modulus of vn's, it converges. Okay, so we have another series which is vn, which is absolutely convergent, plus this sequence which we have here, sequence of un, we know that each and every member, this un, the modulus of this un is less than equal to the modulus of vn. That is, each and every member cannot exceed the absolute value of each and every member cannot exceed the absolute value of each and every of the corresponding member in this particular series. Okay, so if this happens, if that reference series which we know is already absolutely convergent, and this given series each and every member is, it does not exceed each and every member of the corresponding member of the other series, then we say that this series which is given, it is also absolutely convergent. Then if this reference series, if it diverges, okay, and this condition is inverted, that is un is definitely it is greater than or equal to vn for all n, then this un also diverges, but that is modulus un will also diverge, but the original series may or may not converge. Okay, now you can understand why it is called as comparison test, because here we are comparing the given series with respect to some other series. Okay, so the series is given, we find some other series which is already absolutely convergent, and we compare them term to term. If we find that the modulus of this member does not exceed the modulus of the corresponding member in the other absolutely convergent series, then this series is also absolutely convergent. But if the other way around happens, then this the absolute the modulus of this given series will also diverge, but that given series we may not know whether it converges or it does not converge. So that's your comparison test, because we are comparing with some other absolutely convergent series. Next is the ratio test, which is really important. In fact, we use this ratio test everywhere. Okay, in all our problems, so we basically use this ratio test. So what a ratio test is, it says is basically this. Okay, you take the ratio of two subsequent elements in the sequence. Okay, so you take the un plus 1 and un. So for instance, let's say n equal to 2. Okay, so you take the ratio u3 by u2, or if you take n equal to 7, then u8 by u7. So you take the ratio of the two and then take the modulus, and then what you do is you take the limit as n tends to infinity. Okay, so if you take the limit as n tends to infinity and you get some finite value L, okay, then this original series will be absolutely convergent if this finite value L is less than 1. It will be divergent if this finite value L is greater than 1, and if this L is equal to 1, the ratio test is going to fail. Okay, so I'll just repeat again. So what you do is, in the ratio test, you take the ratio of two subsequent members, that is next member divided by the current member, and then you take the absolute value of this one, and then this result, this ratio that you get, you take the limit as n tends to infinity. and if this limit is a finite value, then this original series, it will be absolutely convergent if this L is less than 1. If it is L is greater than 1, then it will be divergent. If L equal to 1, then the ratio test is going to fail, which means we have to try out some other test or some other means by which we can find out whether the series will converge or not. Then we have the nth root test, which is very similar to your ratio test. So instead of taking the ratio of two subsequent members, what you do is you take the nth root of the modulus of the nth element, and again you take the limit as n tends to infinity, and if this gives us a finite value L, then the rest of this is the same. That is, the original series will be absolutely convergent if this L is less than 1, divergent if L is greater than 1, and if L is equal to 1, then the nth root test is going to fail. Okay. Now these are not the only tests for convergence that are available. There are many other tests which are available. For instance, the integral test, the Gauss test, the Rabe's test, or many different tests which are available. But we just need these three tests from the point of view of the problems that the scope of problems that we will be solving. Okay, so from that point of view, we just these are the three most important tests that we'll be using. The other tests, if you are interested, you could just go through this book by Murray Spiegel. It's an excellent book. Okay, it's called Complex Analysis, I think. Okay, it's there in the references. You can go through these books. There it's given in great detail the other test for convergence. Okay, so now moving on, let's take an example. Okay, so we'd like to find out the region of convergence of this particular series. Okay, the series is, that is, un is equal to z plus 1 to the z plus 2 to the power n minus 1, n plus 1 cube, 4 to the power n. So we need to find out the region of convergence here. So here, this is basically your un. Okay, this is your un. So what we'll do is we'll use the ratio test. So what you do is, from this un you find out un plus 1. So that is easy. All you have to do is just replace this n with n plus 1. Okay, so you replace n with n plus 1. So as a result, what happens is there is an n here, so you get replaced with n plus 1. So n plus 1 minus 1 will give us n, and there is another n here, so that n will get replaced with n plus 1. So n plus 1 plus 1 will give us n plus 2, and there is a 4 to the power n here, that n will get replaced with n plus 1. Okay, so you have un plus 1 and you have un. Okay, so this series, we know that it converges at z equal to minus 2, because that's a trivial case. We had discussed this in the class, because at z equal to minus 2, this is going to each and every un is going to become 0, so that we already know. But for the other points, we now try the ratio test. Okay, so for ratio test, what you have to do, you have basically divide this by this and take the modulus. Okay, so when you divide this by this, so we have here, so we'll get z plus 2 to the power n divided by z plus 2. Okay, this 1 second. Okay, so z plus 2 to the power n divided by z plus 2 to the power n minus 1. So this z plus 2 to the power n will get cancelled, and z plus 2 to the power minus 1, which will remain in the denominator, which we can take it up, and it becomes z plus 2. Then this will be in the denominator, and this will be in the numerator, and then we have this 1 by 4 to the power n plus 1 divided by 1 by 4 to the power n, that is simply going to give us 1 by 4. So this is what we will be having. Okay, now as n tends to infinity, this one, so here also in numerator we have cube, and denominator also we have cube. So as n tends to infinity, the numerator and the denominator, that is going to become almost the same. Okay, so because a very large number plus 1 and the same large number plus 2, it remains almost the same. So this ratio is going to give us, is going to tend towards 1. So as n tends to infinity, this is going to give us 1, and as a result, we'll be left behind with only z plus 2 by 4. So z plus 2 divided by 4, and we saw that this is a finite quantity for finite values of z. Okay, so this is our L value. So using the condition for convergence, for the ratio test, we can now find out what is the region of convergence here. Okay, so the series would be absolutely convergent if this L is less than 1. That means if z plus modulus z plus 2 by 4 is less than 1. If modulus z plus 2 by 4 is less than 1, that means 4 goes here. That means z plus 2 is less than 4. Okay, so you here what this means. What does it mean? It means we are talking about a circle, the interior of a circle, right? Because z plus 2 modulus z plus 2. Okay, so here this is the center of the circle. The center of the circle is -2. Okay, the center of the circle is -2, and the radius of the circle is 4. So consider z modulus z plus 2 equal to 4 will give us a circle whose center is at -2 and whose radius is 4. So modulus z plus 2 less than 4 will give us the interior of that circle. So, okay, so we know that the series will be convergent inside the circle, but what about on the circle? Okay, so that we really don't know. So that means the series is convergent inside a circle of radius 4 and centered at z equal to -2. Okay, so this is what we know so far. Okay, but is the series also convergent on the circumference of the circle? So this tells me that it is inside the circle, it is convergent, but what about on the circle? Is it convergent or not? So what is the value condition? On the circle we have z plus 2 is equal to 4. So what we'll do is we'll take the modulus of un. Why are we taking the modulus of un? Because we'll now try to check if this sequence, if it is absolutely convergent on the circumference of the circle. That's what we'll try to find out. Okay, and how do you check if something is absolutely convergent or not? All you need to do is take the modulus of that and then find out if it is really if that sequence of this modulus, okay, sequence of the series of the sequence that you get by taking the modulus of the original functions, if that converges, then it is said to be absolutely convergent. So we want to check if this is absolutely convergent, and then from the theorem of absolute convergence, if this is absolutely convergent on the circumference of the circle, then we know automatically from the theorem of absolute convergence that this sequence will also be convergent on the circumference of the circle. So what you do is you take this un, okay, take the modulus of this. Okay, now what do we get? Okay, modulus of this n plus 1 to the power 3, because n starts at 1, right? So n plus 1, this will always be a positive number. 4 is a positive number, so n plus 1 to the power 3 will be positive. 4 to the power n also will be positive. So we can just take this modulus and apply the modulus on what we have in the numerator. So modulus of z plus 2 to the power n minus 1. Now what is modulus of z plus 2? Modulus of z plus 2 is 4, so we substitute 4 here. Okay, so this will replace 4 here, so 4 to the power n minus 1. So we have 4 to the power n minus 1 divided by 4 to the power n, so 4 to the power n will get cancelled. So in the numerator what we will have is 4 to the power minus 1, so that 1 by 4 will get 1 by 4, so 1 by 4 to the power n plus 1 cube. Okay, and this will be obviously less than 1 by n cube. Why? Because here n cube and this quantity in the denominator is definitely greater than n, right? So this quantity is definitely greater than n, so it will be definitely greater than n cube. So you have increased the denominator, that means you have, if you increase the denominator, overall quantity will decrease. So that means this quantity will be less than 1 by n cube. Okay, so now what will happen as n tends towards infinity? So if I take the limit as n tends to infinity, what will happen? This quantity is going to get smaller and smaller and smaller. So as a result, modulus of un will tend towards 0. So modulus of un tends towards 0 as n tends towards infinity. That means modulus of un, okay, the series summation modulus un, that is going to be absolutely convergent on the circumference of the circle. Okay, so so if modulus un is absolutely convergent on the circle, then from the theorem of absolute convergence, the series also would be convergent on the same circumference of the circle. So we showed, okay, we showed here that the series, it is convergent inside the circle, and from here, from the theorem of absolute convergence, we have shown that it is also convergent on the circumference of the circle. That means it is convergent everywhere on the circle. That is, it is convergent on the it is convergent on the circle as well as it is convergent inside the circle. So the region of convergence will be z plus 2, modulus z plus 2 will be less than equal to 4. So that this is one example how we can obtain the region of convergence using these different theorems of convergence. So now this is an exercise which I've left you, just 2 problems. You could just get a feel of how to solve problems like this. Just find out what is the region of convergence. If they don't converge, I mean if they diverge, okay, you just mention that. Okay, so that's your first exercise. So I'll leave this to you as an assignment in the Google Classroom. Okay, so we'll now go to the power series. Okay, the power series, basically any series that has this form is a0 plus a1 z minus a plus sorry, there's a mistake here which I'll have to correct. This is a2, this must be a2 z minus a square and so on. So in other words, we could write a power series as this: a n z minus a to the power n. Okay, there is un, the sequence. In general, we have taken summation un is nothing but a n z minus 1 z minus a to the power n. So this kind of a series is known as a power series in z minus a. Okay, so if the power series converges at points other than z equal to a, then we can show that there exists a positive number r such that the series converges for z minus a less than r and diverges for z minus a greater than r, while for z minus a is equal to r, it may or may not converge. Okay, so because this z equal to a, it's a trivial case, because if I take z equal to a, this is going to be 0, then all the u's will be 0, then obviously the series is going to converge. Okay, so apart from z equal to a, if there are at least one other point at which the series converges, then we can show that there exists a positive number, some positive number r exists such that the series converges. Okay, so using this r, you can create a circle whose center is at a and radius is r, and you can show that the series, it converges inside the circle and it diverges outside the circle, and for on the circumference of the circle, it may converge, it may not converge. So that's where we'll have to resort to some other means to find out whether it converges on the circumference or not. Okay, so if C is a circle of radius r and it is centered at z equal to a, then r is known as the radius of convergence, because you can see here from this condition here, right, because here we are talking about a circle, so r is known as the radius of convergence, and this c is known as the circle of convergence. Now some theorems on the power series. A power series, it converges uniformly and absolutely in any region that lies entirely inside its circle of convergence. Okay, so if I have a power series and I know what its circle of convergence is, then the power series is going to converge uniformly and absolutely within that region which lies inside its circle of convergence. Okay, so I hope by now you're familiar what this means. Basically, it is uniformly convergent and it is absolutely convergent. Okay, so I've already discussed what is a uniform convergence and what is absolute convergence. Okay, so if a power series, it is guaranteed, okay, if it has got a circle of convergence, okay, if it has got a circle of convergence, then in the region which is contained by the circle of convergence, the power series, it is guaranteed to be uniformly and absolutely convergent. Then the theorem 2, it's the first part of theorem 2 is, it says that power series can be differentiated term by term in any region in which lies entirely inside its circle of convergence. So inside a circle of convergence, a power series, you can just differentiate it term by term. And you could also integrate the power series term by term along any curve which lies inside the circle of convergence. So I have a circle of convergence. Inside the circle of convergence, you take any closed contour on this closed contour, or it could be an open curve also. Okay, on any curve which lies totally inside the circle of convergence, you can just integrate the power series term by term. Okay, and the sum of the power series, it is continuous in any region which lies entirely inside its circle of convergence. Okay, so I think we'll take a break here, and in the next lecture we'll come back and we'll discuss the Taylor's theorem.